3.9, we're talking about differentials. And to start out, to describe what differentials are, is we're going to talk about linear approximations. And what linear approximations are is we can use a tangent line to approximate where a point is on the graph. And that only makes sense. What a tangent line is a line that meets our graph and it hits it only at one spot. So if I were to draw some graph like this, okay, and I wanted to know what the value for y was at 1, where x equaled 1. So what we could do is we could find the equation of the tangent line, and we can plug it in right here and get the equation of the tangent line. And we're saying that what a linear approximation is saying is that as our x values get closer, so if we're plugging x values into our tangent equation, their x values get closer and closer to our actual x that we want, all right, on either side. As they get closer and closer to this original value right there, I think we called it 1, all right, our value for y is going to get closer and closer to what the actual value for y is as well on the graph. If we were to just plug it into the equation, we'd get it, all right? And I know you're probably thinking, well, why don't we just plug it into a regular equation? We can tell. But this is setting up what differentials are, and you'll see how we use it in a little bit. So what I have here is, hopefully you remember point slope form, and this is where this all came from, point slope form. So we're going to use point slope to find our equation of a tangent line. And that's where point slope, that is what point slope form is. Actually, now that you're in calculus, you know where that came from, all right? It's the equation of a tangent line, really. All right, so you're finding the slope, you're picking a point, it's going to be the equation of the tangent line at some point. The reason why that's never explained to you is because before calculus and pre-calculus, and maybe a little bit in algebra 2, you started using graphs that were curved, all right? So we're going to start looking at how we use the point slope form to write our equation of tangent line and use that for linear approximations, okay? So here's our first example. It says find the tangent line approximation of f of x equal to 1 plus sine of x at the point 0, 1. Then compare the tangent approximate to the real value of f of x. Well, all right, let's go ahead and let's write the equation. So basically they're saying write the equation of the tangent line to this graph, 1 plus sine of x at the point 0, 1. So we're going to write our equation at the point 0, 1. All right, so I need this. First of all, I need my slope, right? So to figure out my slope of any point in that line, we take the derivative, right? That's how we get slope. That's going to be the slope of the tangent line at any point. So let's take the derivative. So f prime of x is going to equal, the derivative of 1 is 0, and the derivative of sine is cosine. All right, so now we can figure out our slope. Is our slope, then we can plug in our x value and get our slope. So our point is 0, 1, so we're going to plug in 0 for x and get our slope to be the cosine is 0. The cosine of 0, you should all know from pre-calculus, is 1. So our slope is going to be 1. So now let's write the equation of our tangent line at this point. So we have y minus 1 equal to 1 times x minus 0. All right. And so I have y minus 1 equal to x. So our equation for our tangent line is x plus 1, y equal to x plus 1. And we're saying now is we can use this equation y equal to x plus 1 and get points closer and closer to 0, and it should come out that if as we're getting closer and closer to 0, so if I pick like negative 0.1 and then negative 0.01, as we get closer and closer to 0 on either side, all right, our value for this guy is going to be awfully close if we were to just plug in 0 into the original equation. Let's plug 0 into the original equation and see what we should get. What would our y value be if we plug 0 in? So we'd have 1 plus the sine is 0. The sine of 0 is 0. So our actual, it should be 1, right? 0, 1. That's where we get the point. Okay. So I'm going to show you the chart down here. Here's our tangent line approximation at that point. That's the equation of our tangent line. I have it right here. There's the equation of our tangent line. Here's the original equation. If I plug in negative 0.1 into my original equation, I get 0.9002. If I plug it into my tangent approximation, I get 0.9. Awfully close, right? If I plug it in, get even closer to 0, I get 0.99. It goes farther out, and in my tangent approximation, I get just 0.99. Pretty darn close still. Okay, and then we plug in 0 with both of them, we're going to get 1, and that's what we should get. So what I'm showing you is that we can use a tangent line to approximate where our y value is on a graph. And what comes out of that is the differentials. All right, the definition is let y equal to f of x, some function represent a function that is differentiable in an open interval containing x. The differential of x, which is called dx, is any non-zero real number. So basically they're talking about the change of x. Okay, the differential of y is, well, dy equals the derivative with respect to x times dx. This goes back to earlier when we were implicit differentiation. Okay, so we use differentials to approximate the change in y opposed to finding the actual change in y because it's oftentimes easier. What the change in y is we're talking about is if we have 2 points. Let me just draw a graph here like that. If we have 2 points, pick like 1 and 1.5 or something. Okay, to find the change of what y does, all right, you'd plug in, here's 1. Our change of x is going to be 0.5, so we'd have our f of x plus our change of x, so 1.5. And this isn't really making sense. I kind of confused myself here in a little bit. Okay, so my change of y. Oh, here we go. Okay, so my change of y is what I'm doing is I changed y by 0.5. Okay, so what this becomes is f of 1.5 because that was my change of x. So I'd have my original one was 1. I changed it by 0.5. So my f of x is 1.5, and then to figure out my change of y, then I subtract it by f of 1. So to figure out what my y did from here to this point, I'm subtracting the value here. So this value of y minus that value of y, and that should be the change, how much it changed. That makes sense, right? Sorry, I confused myself for a second there. Okay. So here we go. We have an example showing you why it's easier and why it's pretty darn close and why we use differentials instead. So we're saying let y equal to x squared. Find dy when x equals 1 and dx equals 0.01. Compare this value with change of y for x equal to 1 and x equal to 1 and change of x equal to 0.01. All right, so let's use our differential. Let y equal to x squared. So let's take the differential of it. So we're taking the derivative with respect to x. We're going to say dy equals 2x dx. Okay, so then they want us to find dy when x equals 1. So we're going to go ahead and we're going to plug that in here. And when dx equals 0.01. And I have to pause this for a second and get my calculator. So let me pause this quick and I'll be back. Okay, so here we go. And actually in this first part I'm not going to need my calculator. In the second part I might a little bit. So here what we're going to do is we're going to plug those in. So I'm going to have 2 times 1, I'm plugging my x value, 2 times 1 times my dx, which is 0.01. So I'm going to have 2 times 0.01. When we multiply those two, it's just 2. Don't forget our decimals, so we got to move our decimal place over 2 spots. So 0.02. All right, so there's our differential at that point, x equal to 1. Our differential is going to be 0.02. Well, let's compare that then to the old way of finding change of y. So it would be f of x plus change of x minus f of x. Okay, so if we go ahead and we plug in f of x plus change of x, okay, so we'll have 1 plus 0.01. That was my change of x up here. Here's my x. Here's my change of x. Okay. Or sorry, here's my change of x down here. Okay. And then I'm going to subtract then f of just 1. Okay, so I'm going to have f of 1.01 minus f of 1. So if I plug 0.1, this is where so I'm going to have 1.01 squared minus, and then when I plug 1 into the original equation, I'm just going to get 1. When I square 1.01, I'm going to, and then I subtract 1, I'm going to go ahead and I'm going to get 0.0201. Notice how ridiculously close that is, all right, and how much easier it is just to take the differential and figure out it that way. Okay, so there's that problem. We were comparing those two. All right, and our last one here, our last problem, I gotta get that thing back up here so I can see if I have enough time. This last problem here I'm going to do in a separate video because we're running out of time here. Okay, so we'll see you in another video.